In this video, I'm going to present our work on parallel self-assembly with SMORES-EP, a modular robot. There have been more and more modular robotic systems being developed. These systems are usually in three types. Chain type, like the polybot. Modules can form chains to be in many morphologies. Lattice type, like robot pebbles. Each module occupies a regular space, such as a cubic grid. And mobile type, like kilobots. Modules can use the environment to maneuver around and come together to form some complex patterns. Some systems can be in all of these types, which are hybrid systems, such as the robot we use in this work, SMORES-EP. The main advantage of modular robots over other systems is the flexibility. Tasks can vary a lot, and the robot morphology may be good for some tasks, but not for something else. For example, there are some candies on this table, but this is too difficult for these two kids to get them. However, it is easy for this adult. The adult is very tall, but it is hard for him to get the key below this table. Well, it's very easy for this baby if he knows how to do it. This characterizes the key features of modular robots. Modular robots can change their morphology to best satisfy different tasks whenever needed, and this relies on self-reconfiguration and self-assembly ability. In this work, we focus on self-assembly behaviors to enhance the capability of the system. In robotics, we have been inspired by collective intelligence in nature. For example, a SMORES-EP module cannot overcome its gap, because this gap is too wide to go across. However, three modules can come together to form a small vehicle to overcome this gap. This really increases the capability of how robots interact with the environment. In this work, we present a framework to allow modules to form useful kinematic topologies in order to execute tasks which cannot be done by any individual one. The robot we use is SMORES-EP. Each module has 4 degrees of freedom and 4 connectors. There are in total 17 different ways to connect the two modules. This gives us a lot of versatility to form many different morphologies, but this also brings about challenges to handle this large number of possibilities. Each module can behave as a vehicle, and this allows multiple modules to self-assemble into a whole structure. We use a graph to describe a target kinematic topology, which is a modular robot configuration. We focus on tree topology in this work. For each target topology, we can compute the root module in linear time using our previous work. For example, for this simple configuration, we can compute the root module efficiently, and the result is module 2. Then, given a cluster of modules in the environment on the left and a target kinematic topology on the right, we first need to assign each module a role in the target configuration, which is a task assignment problem. What we have to do is to unfold the target configuration to the ground, compute the root module, and calculate the relative position and orientation of every other module with respect to this root module. Given the locations of our modules in reality, we find the module in the center or closest to the center. This module is assigned as the root module. After this, we can apply Pull-Moncrief's algorithm or other capped algorithms to find the optimal solution to this task assignment problem with respect to some cost function. In this work, we try to minimize the total distance that modules have to travel. With the optimal assignment, parallel assembly can start. Each assembly action is a tuple shown here. The assembly process starts from the root to leaves. Modules with the same depth in the target configuration can move in parallel to execute assembly actions. The special case is for root module. The root module is not fixed on the ground, and it is hard to guarantee all modules attached with root modules can execute docking process at the same time. Hence, we do assembly actions with left face or right face first, then top face or bottom face. This behavior will be seen in our experiment. The paths for active modules in each step can be computed by some well-developed multi-vehicle planner. Docking is usually a hard and time-consuming task for modular robots. In order to execute docking process, each module first navigates to a location close to its mated module using a differential vehicle controller, then start to precisely adjust its pose for docking with the feedback controller shown below, and align the involved connector accordingly. Finally, approach the mated module and activate connectors for docking. The special case is when left or right face of the moving module is involved. Left face and right face are used as wheels for driving, so we cannot align these two connectors directly for docking. In these cases, we design a helping module which can approach the moving module, lift it up so that the connector can be adjusted and delivered to the target location. Here we show the docking process step by step. We first navigate the module to a location close to its goal. Then adjust its pose and align the corresponding connector if necessary. Finally, approach the mating module while maintaining its orientation. And then execute docking action. Here are the performance of our docking controller. The pose can be adjusted quickly and approach to the destination while keeping the orientation fixed. This control process can guarantee the success of docking. Here is our first experiment to self-assemble into a mobile manipulator so that they can reach a high location. In our experiment, we use a Vicon motion capture system to localize the locations of modules. The second one is to self-assemble into a holonomic vehicle to quickly explore an area. The last task is to self-assemble into a RC car in order to push some heavy objects, and a helping module is used. Thank you for watching.